These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. So let's see, we have one current carrying wire that's pointing to the right and one current carrying wire that's pointing to the left, and we're trying to figure out the directions of the electric fields, say over here. Okay, well, why don't you tell me how you would go about doing that, and we'll see where the problem is arising. So how would you think about that?
Okay, so since it's a current carrying wire, I would use this one.
Right.
So my thumb points, if I want to know the magnetic field from the top wire,
Good.
My thumb points this way to the right.
Good.
And my finger pads point the direction of the magnetic field.
Good.
So it should be coming out of the page.
Okay.
Right?
Yeah, let's talk about that.
Okay.
So I'm glad that you brought that up. That's important to clarify. Okay, so it's good that you're using the handout that we went over last time. I want to get in the habit of doing that. So that's that magnetism handout. And we know that has a left side and a right side, but we're treating this like a source current because we want to know the magnetic field from it. So you're using this part of the handout. So that's good. Now you're using your thumb to point, and you're thinking about this separately. So that's good. You're just trying to figure out the current from the top wire. So your thumb is pointing to the right. Now the one thing that you've missed from the handout is before you can interpret your finger pads, you have to position your fingers in the location that you're interested about. So for example, in this case, should my fingers be above my thumb, or in front of my thumb, or below my thumb, or in back of my thumb? We want to put our fingers in the location that we care about, and to figure that out, we don't want to, and now we're done with the handout and we have to consult the problem.
Yeah.
So here's the wire, and that's represented by my thumb. Now, are we interested in a point that's above the wire, in front of the wire, below the wire, or behind the wire?
Below the wire.
Below the wire. So that's where you have to put your fingers. So notice that there's many different places I can put my fingers and still have my thumb pointing to the right. But I have to put my fingers below my thumb so that I can figure out the direction of the magnetic field that's below the wire. Does that make any sense?
Yeah. So I'm pretending my hand is the wire, I'm pointing my fingers in the direction of the...
In the location that you care about.
The
That's right.
Or whatever.
Just in the location of the
Yeah.
point in space that we're looking at. So again, yeah, so we're pretending that your thumb is the wire. Your thumb is the wire. Well then, we could try to figure out the direction of the magnetic field above the wire, or in front of the wire, or behind the wire, or below the wire. Well, in this particular case, we want to be below the wire. So let's try that and see what that gives us.
Okay, so it's pointing this way, but the charge is below the wire, so I put my fingers down. So I guess my finger pads are pointing into the board.
Into the board.
Okay.
That's right. So now, let's give these some names. So here we would have the magnetic field from wire 1. That's pointing into the board. Okay. Yeah, so it's good that we had a chance to go over that again. So the part of the handout that's to remind us of that is before we can use this, you have to put your thumb in the location of the source current and put your fingers in the location of the magnetic field. Might not have been clear what that meant, but now we've kind of gone over that.
Okay.
Notice that that is something that doesn't apply to the right-hand rule over here. For the right-hand rule for determining force, we don't have this idea of location anymore. But when we're trying to figure out the magnetic field, well, the magnetic field is different in different locations. So before we can use the right-hand rule, we have to put our fingers in the correct location relative to our thumb. Okay, so we decided that now this is going to be pointing into the page. Well, for practice, let's try to figure out the magnetic field from this current.
Okay, so now the current's going to the left.
Right?
And the point's up. So my fingers are pointing up, so it's going into the board as well.
Yeah. Now my thumb represents I2. Well, I could put my fingers in many different places relative to my thumb, but I want to put them above because this position is above I2, and now the finger pads are pointing into the page. And you remembered from last time that when we use this right-hand rule, we focus on your finger pads, not your fingertips. Our finger pads are pointing into the page. So what about the net magnetic field here? What direction is that in?
Into the board.
Because these two would reinforce each other.
Yeah.
Okay, yeah, so it's good that we had a chance to go over that. So that was one technique that you weren't clear about yet, but it's good that you are clear about a couple of other things. For example, you knew which right-hand rule to use. You knew to use this one and not this one, so that was good. And also, one thing that you did that was very good is that you thought about the two currents separately. First, you thought about the magnetic field from this current, then you thought about the magnetic field from this current, and only then did you add them together. I'm glad that you're thinking about that because we didn't have a chance to talk about that the last time we met. All the examples I gave you, there was only one wire at a time, but you figured out if there's more than one wire, you just think about them each separately and then add those things together.
Mm-hmm.
Okay, good.
Okay. So I guess that's the question I had about that. So maybe then for B it says find the direction and magnitude of the forces on the electron.
Right.
So maybe we could try for that.
Okay, so do you want to just try a problem?
Sure.
Okay, all right, well, as long as we're doing that, I guess we might as well. So let's see. We've got our two long straight wires. And they gave us these axes. One part of part A was, are there any electrical forces on the electron?
Mm-hmm.
So how would you answer that?
Well, so if it's an electron, it's negatively charged. So
That's
you
true.
know that any electric field would be pointing towards the electron. So you know that by symmetry that there's no electric field.
Okay, well, okay, we should talk about that because it turns out that actually isn't the right framework to think about that. So let's go back.
Just think about how there's like an electric field coming down and then an electric field going up and they cancel.
Okay, yeah, it turns out I think that's not right. So let's see. So what the first thing you're trying to do, so first of all, we know we have an electron here. Now, how are we treating the electron? Like a source charge or a test charge?
Like a test charge.
Yeah, because we want to know if there's a force on the electron.
Mm-hmm.
Okay, and now, so you were focusing on these as possible source charges. So that was good. But the problem is that you were thinking of these as being full of electrons. I think you were kind of confusing this electron with the wires. It's true that over here there's an electron, but that doesn't mean that we should think that these have surpluses of electrons. So let's think about the wires all over again. What is the net charge on this wire? Is it positive, negative, or zero? What's the net charge on this wire? If this is just an ordinary wire, would it be positively charged, negatively charged, or zero charge?
I'm not sure.
Well, normally things are neutral. Most things are neutral unless we have stripped some electrons away from them or put extra electrons onto them. So normally things are neutral. Let's actually step back from this because this is a complicated problem and just think about wires in general.
Okay.
So so the key thing is, where do electric fields come from? Electric fields occur when you have a net charge. That is when you have more positive charges than negative charges, or more negative charges than positive charges. However, a normal wire has an equal number of positive and negative charges. For example, you know, in normal chemistry, we think that every atom has the same number of protons as electrons, and everything balances out. The normal thing is for things to be neutral. If you just look at an ordinary wire that you're using in a circuit, that would be neutral. Most wires are neutral. So it's true that there's a bunch of electrons on here, but there's an equal number of protons. And so the protons and the electrons are going to cancel each other out. So there's actually no electric field at all coming from this one. That's a good question. There's an equal number of protons and electrons here. However, remember, a current is when some of the charges are moving. So there's an equal number of protons and electrons here. However, only the electrons are moving.